let me remind you that last time we talked about such important things as conditional probability independence, total probability, and Bayes' rule. Okay? Today we'll start with so-called rules of counting. First, let's discuss this example. In a certain club, there are 10 members. Club, 10 members. And at their first session, the members have to elect the governing officers, the president, treasurer, and secretary. Now, so there are 10 members in total, and these 3 posts for which some persons have to be elected. Let's ask this question. Suppose Smith, Brown, and Jones are 3 of the members. What's the probability that these 3 members will be, well, suppose the positions are filled at random, okay, which is not typical for this kind of this thing, such as electing the governing bodies. But let's assume that the members of this club believe in random choice. Maybe it's the club of lovers of probability theory, maybe, I don't know. So what's the probability that Smith will be president and Brown will be treasurer and Jones will be secretary? Okay. Now, this event contains just one outcome. This is an event that consists of one outcome. And how many outcomes are there in total? In how many ways can we select in a random way 3 individuals out of a total group of 10? Well, no, not 9. Let's reason this way. Suppose we first want to fill the position of president. Okay? In how many ways can we do this? There are 10 members in this club in total, so there are 10 possibilities for filling this position. Okay? And the next logical step is the most important here. After we have made a decision on this position, how many options do we have left? How many candidates are there for the second position? 9. There are 9 options left. And what's important to understand, any choice that we can make here can be combined with any choice that we make for the next position. So there are 10 times 9 ways we can fill these 2 positions. It's an important logical step. Do you have any questions about this? Okay. And after we have filled these 2 positions, how many options do we have left for the third one? Obviously it's 8. Okay? And again, any choice that we make for the first 2 positions can be combined with any choice here, so we multiply. And this is 720, and this is the total number of outcomes here. Okay? But it's important to understand this. Smith president, Brown treasurer, and Jones secretary is not the same as Brown president, Smith treasurer, and Jones secretary. Do you understand this? So we talk about ordered selections. Ordered selections. The order is important here. we consider as different selections that only are different in terms of order. Get this? All right. Now, generalizing from this example, we write this formula. Number of permutations, and this is, may I ask you to keep quiet, you personally, okay? This is a new word, a scientific kind, the word permutations. And the explanation is ordered selections. The number of permutations of n objects taken R at a time. Well, generalizing from this, reasoning in the same way, it's this. Now, the standard notation is this, and it's n for the first choice that we make, then it's n minus 1, and so on. And what's the last term? Is it n minus r? Okay, we need to have r terms in this product, and we'll have r terms if the last term is n minus r plus 1, not n minus 1, n minus r. Okay, an important particular case here is this. Suppose n equals r, like this. So it's the number of ways we can arrange n objects. And it's n times n minus 1 times n minus 2 down to 1. And there is this special notation for this product. It's called n factorial. This symbol that looks like an exclamation mark means exactly this, multiplying all the integers from 1 to n. All right, I hope it's clear enough. Let's give it some simple examples. Well, suppose we have 5 people. 5 people, Adam, Bob, Colin, Ben, and Ed. I write these names especially to emphasize that these people are all different. We know their names. We differ. We distinguish among them. And the question is this: in how many ways these 5 different people can be seated on 5 chairs that stand in a row? 5 chairs in a row. And why do I add this in a row? Again, I want to emphasize that we distinguish among the chairs. We know that this is the first chair and this is the second chair, and okay, all of them are different. So in how many ways can 5 people be seated on 5 chairs? It's exactly this case. The answer is the number of permutations of 5 objects. So here it's 5 factorial, which is 120. If you multiply 1 by 2 by 3 and so forth, so on, up to 5, this is the answer. Well, for the same setting, so this is part A of this example. For the same setting, let's ask a slightly different question. Suppose Adam takes the first chair, and Bob takes the second chair. Okay. Suppose we know that. So again, 5 people sit on 5 chairs, and now the arrangement is not exactly random. We know that Adam takes the first chair and Bob takes the second chair, but the rest of this arrangement is still random. In how many ways can this be done? Okay, what remains is 3 people sitting on 3 chairs. So it's the answer is 3 factorial, which is 6. Okay. Now let's ask this question. Suppose these 5 guys sit on 5 chairs in a random way. What's the probability that Adam finds himself on the first chair and Bob finds himself on the second chair? Now the answer is this: probability Adam first and Bob second is 3 factorial, which is the number of ways the remaining 3 guys can sit on the remaining 3 chairs, divided by 5 factorial, which is the total number of random arrangements. And this is 6 over 120, or 1 over 20. Okay? A simple example. Okay. Let me emphasize again that here we talk about ordered selections. This is an important word here. And now let's talk about unordered selections, which is also something that appears quite often in probabilistic problems. Let's discuss this example. A tea merchant has 10 pure teas in his stock. 10 pure teas. But this tea merchant doesn't sell pure teas. Instead, he makes mixtures. And the mixture is made by mixing equal quantities of 3 pure teas. Okay? So this is this is what this merchant does. He mixes equal quantities of 3 of these pure teas and gives some attractive name to this mixture, such as princess or tiger or rose or something else. Okay. The question is this: given that the total number of pure teas is 10, how many different mixtures can this merchant produce? Let's try to reason. Well, do you notice that the numbers are similar to the numbers that appeared in the club example? And I selected the same numbers on purpose. I wanted these 2 examples to look similar. And let's try to reason in the same way. Suppose we are making a mixture. In how many ways can we select the first pure tea? There are 10 of them in total, so there are 10 choices for that. Okay? Okay, suppose we take 1 kilogram of one of the teas. And then we need to choose 1 tea out of the remaining 9 pure teas. Okay? So it's 10, and then it's 8. And this product is 720. Is it the right answer here? It was the right answer when we talked about electing the president, secretary, and treasurer of a certain club. But is it the right answer here? Or is there some problem? I'd like you to understand, to see that there is a problem here. Something is not quite correct. And the problem is this. Suppose the first choice was tea number 1, and the second choice was tea number 5, and the third choice was tea number 9. I just pick some numbers at random. What I mean to say, suppose we choose number 1 when we select the first tea, number 5 is our second choice, and number 9 is the third choice. Well, and now let's look at this. Suppose our first choice is number 5, and the second choice is number 9, and the third choice is number 1. Is it a different mixture? It's the same mixture if you look at these T's. One is here, one is present here. T number 5 is present here and is present here. And number 9 is also present in both mixtures. So, in this way, we produce the same mixture twice. But the question is this: do we count these two mixtures as distinct here or not? The answer is yes, which means overcounting. We count the same mixture more than once if we just multiply 10 by 9 by 8. Okay? Question: how many times will the same mixture be counted in this total quantity? How can we compensate for this? Now the answer is this: the same mixture will appear in this total quantity as many times as the number of times we can rearrange these three pure T's, which is 3 factorial. It's the number of permutations. So to get at the right answer, we need to divide this by 3 factorial, okay? Which will give us a different thing, not the number of permutations, and permutation means an ordered selection. Now, what we get now is the number of combinations, and combination is an accepted term for unordered selection. Okay? So the answer here is 10 times 9 times 8 divided by 3 factorial, and this is 120. Okay? Well, again, generalizing from this example, let's write the general formula. Number of combinations or unordered selections of n objects taken R at a time. Well, there are more than one accepted notation for this. This is one of them, which is similar to this. But more popular is this one. Okay? And the formula is this. It's n times n minus 1 and so on, n minus r plus 1 divided by r factorial. Well, and this is the right formula, but because it's a bit long, quite often another version of it is cited. If you multiply and divide this fraction by n minus r factorial, this is what we get. I don't have any space left here, so let me cite it here. It's n factorial divided by r factorial by n minus r factorial. Okay. So this is our formula. In probability theory, it's a very important formula. It appears quite often. Something very, very fundamental. Well, and because it appears so often, there is a popular common name, not a formal name for it. Rather than saying all this, they say n choose r. Okay? It's an informal way to refer to this formula. N choose r. Any questions here? Well, let's give it a couple of examples. Well, In a student group of 15, a certain project is assigned to 6 students. In how many different ways can this assignment be made? So, 15 students, and 6 of them are assigned to a project. Okay? So what's the total number of ways this assignment can be done? Now, a comment is necessary here. What I'm going to write now relates to the case, to the situation where the 6 students selected for the project are all equal. There are no leader and no vice leader or anything. Okay, they are all equal. They have equal status. So if this is the case, then the answer is 15 choose 6. We can write it this way, or we can write it this way. Let's write it this way: 15, 14, 13, 12, 11, 10. And we divide it by 6 factorial. Well, let's write it out too. It's 1, 2, 3, 4, 5, 6. So the numerator is this kind of product, and the denominator is the factorial of 6 here. Look at this expression. It looks rather formidable at first, difficult to handle. But actually, you can notice that a lot of cancellations are possible here. So you can work this formula even by hand without a calculator. And the answer is 5005. Okay? Well, let's consider a slightly different example, a more developed version of the same example. So in a student group of 15, there are 8 girls and 7 boys. 8 girls and 7 boys. And the same thing happens. The teacher assigns 6 students to do a certain project. The question that we want to ask now is this. So let's write this down. 6 students are assigned to do a certain project. Suppose this assignment is done at random. So the teacher doesn't really select the students. The choice is made on a random basis. And if it's a random choice, what's the probability that exactly 4 of these 8 girls will be assigned to the project? So what's the probability that 4 girls are assigned? Okay. Well, it's not as simple as this. So let's reason. First, well, because it's a random choice, the answer will be a kind of fraction. The denominator is the total number of possible choices, and we answered this question just just here. It's 5005, which is the total number of the total number of choices, the total number of ways 6 objects can be selected from 15 if the order is not if the order is neglected. All right, and what is the numerator here? This is the interesting part. First, let's ask this question. In how many ways 4 girls can be chosen out of the total number of 8 girls? And this is again a case where we apply this formula, the combination formula. It's going to be 8 choose 4. Well, do you understand this bit? But then the next question is this. If 4 of those chosen to do the product are girls, then how many boys are assigned? The total number of students to be assigned to this project is 6. If 4 of them are girls, then the remaining 2 are boys. Okay, and we need to choose 2 boys out of the total of 7. So the total number of ways 2 boys can be selected out of the total number of 7 boys is 7 choose 2. But what's important and what I want you to understand, that we need to multiply this number by this number to get the right answer to the question in how many ways 6 students can be assigned to this project, given that 4 of these 6 are girls. Do you understand this? Not a very simple question, but this is about the size of the problem that you are going to do on your course. All right, and writing out each of these, we get at this answer. It's okay. Just for you to complete this at home and check your answer. Okay. Any questions for this part? No. All right. Then the next thing is multiplication rule. Suppose we have 2 sets, A and B. This notation, this is multiplication sign, stands for the so-called Cartesian product. Cartesian product, and this name actually is a derivative from the name Descartes, Descartes was a famous French mathematician. Cartesian product. And by definition it's this. It's the set of all possible pairs AB, where A belongs to A capital and B belongs to B capital. Okay, simple enough, but this idea, this concept appears in many branches of mathematics. Now, suppose both sets are finite. Okay, if both are finite, then the number, then this Cartesian product is also finite, and the number of elements in the product is equal to the number of elements in A times the number of elements in B. Again, simple enough. Let's give it some very simple examples. Suppose a code consists of two elements, two parts. First is a decimal figure from 0 to 9, and second is a Latin letter, one of the 26 Latin letters. So it's a figure and a letter. How many different codes are there? Well, it's a very simple question. The number of codes is 10, which is the number of different decimal figures. Again, 0, we include 0, 0 to 9, 10 figures is multiplied by 26 letters, and this is the answer. Simple enough. But there is a subtle point here. We consider codes where these elements are arranged in this order: figure, letter. We do not admit codes that contain the same elements in a different order: letter, figure. We just exclude this. Okay? And second, let's consider this other code. and this code consists of 2 Latin letters. How many different codes are possible here? And the answer is 26 times 26, which is 676. Again, a reservation must be made here. This is the right answer if AB and BA are considered as different codes. Okay? No questions here? Okay. Right. Now, this leads us to the concept of composite experiment. Well, example. Suppose we do 2 things. We toss a coin and then roll a die. Toss a coin and then we roll a die. Okay. Well, these 2 acts can be considered as one composite experiment. Okay. And how many different outcomes are there in this composite experiment? So this is this first stage, or the first experiment, has only 2 outcomes. It's either heads or tails. And this second experiment has this sample space consisting of 6 outcomes. Okay, so I use this notation: omega 1 for the first sample space and omega 2 for the second sample space. But now we are talking about this whole big composite experiment. How many different outcomes does this composite experiment have? Now, the omega, the sample space for the composite experiments, is the Cartesian product of the 2 sample spaces. Okay, and this product contains such outcomes as H1, for example, and H2, and tails 1, and tails 6. Okay, I'm not writing out all of them. How many are there? How many different outcomes are there here? I mean, this big omega. Here we use this simple formula. Where is it? This one. This one. So n. Okay, if we refer to the number of outcomes in the first experiment as n capital 1, and the second as n capital 2, the total number of outcomes in the composite experiment will be the product of n1 and n2, and here it's 2 times 6, which is 12. Okay. Again, please notice that we consider these 2 stages of the composite experiment as being performed in this fixed order: toss a coin, roll a die. Okay. Well, now let's talk about independence. Now let's assume that the stages of the composite experiment are independent. So suppose the stages are independent. Okay, which means that let's write it this way. Suppose a particular outcome, omega 1, omega I, that can occur on the first experiment. Well, I don't really like this notation. It's a bit awkward, but I don't know how I can write it in any different way. So this one belongs to omega 1, and some outcome omega j with subscript 2 belongs to omega 2. So the simple meaning of it is this. Suppose we look at one of the outcomes that belongs to the first experiment, first omega, and one of the outcomes that belongs to this other omega. Now, what's the probability that the outcome on this composite experiment will be this omega, this omega on the first experiment and this omega on the other experiment? Well, if we assume that the two stages of this complex experiment, the two partial experiments, are independent, then we assume that this formula works. Okay? So if the various stages of a composite experiment are independent, then the probability of each outcome on the complex experiment can be computed as the product of individual probabilities. Okay? Well, let's ask this question. Is it always true that the various stages of a complex experiment are independent? Can you think of a situation where it's not true? Well, quite often, especially in textbooks, in textbook situations, quite often the stages, the individual stages of a complex experiment are independent, and this is the simple situation. But in real life, it's not at all always so. Well, think of a sportsman who shoots at a target several times in a row. It's the same sportsman and the same target. But can we expect that the result on the second shot will be independent on the result on the first shot? Well, I am no sportsman, but my guess would be that there is a dependence here. If the sportsman is successful the first time, probably he will be high-spirited, he will be optimistic the next time, which will affect his result. If he fails the first time, then probably there will be some effect on the second shot. Well, this is what I expect. I don't know what really goes on in reality. Well, you all know that now these Olympic Games in Russia are going on, so this is this may be a practical question. All right. So what I wanted to say is that the various stages in a complex experiment are not always independent, but for classroom situations they often are. All right, and then as an additional assumption, let's assume that well, each sample space of the composite experiment is a finite sample space consisting of equally likely outcomes. So omega 1 and omega 2 are finite and consist of equally likely outcomes. Okay? Again, this is a very strong assumption. It's not at all always this way. But if this is true, now suppose suppose n capital 1 is the number of outcomes in the first sample space, and n capital 2 is the number of outcomes in the second sample space. Because we assume that the sample space consists of equally likely outcomes, the probability of each outcome in this sample space is equal to 1 over n capital sub 1, and the probability of each outcome here is 1 over n capital sub 2. But what about the probability of each? Now, the composite sample space, which is a Cartesian product of these two sample spaces, is also finite, and it also consists of equally likely outcomes, provided these two experiments are independent. This is something that we just discussed. So if the two partial experiments are both both have finite sample spaces with equally likely outcomes, and assuming on top of that that the two experiments are independent, we get this conclusion, that the resulting sample space, which is the Cartesian product of the two, is also finite. It also consists of equally likely outcomes, and the probability of which is this. So now this one belongs to the resulting sample space, which is the Cartesian product, and it's this. Okay, let's give it an example. So a die is rolled twice. How many outcomes are there on this composite experiment? The composite experiment here consists of two partial experiments. We roll a die, and then we roll the same die again. Well, it's a very simple question. Obviously, it's 6 by 6, and it's 36. Okay? And the probability of each outcome here is 1 over 36. Let's ask a slightly more substantial question here. What's the probability that on this composite experiment, what's the probability that the sum is 7? Is 7. Okay. So we roll the die 2 times, and what's the probability that the sum is 7? Well, all we need to do to answer this question is to count the number of outcomes for which this is true. So there are 36 outcomes in common, and what is the number of outcomes for which the sum is 7? How can we get a sum of 7 anyway? 1 and 6 is 7, and 2 and 5 is 7, and 3 and 4 is 7, and 4 and 3 is 7, and 5 and 2 is 7, and 6 and 1 is 7. I want you to notice something important here. We consider 3 and 4 and 4 and 3 as different outcomes, and they are different. And they are distinct in this total number of outcomes of the composite experiment. It's very easy to make a mistake here, okay? It's very easy to consider these two as the same outcome, but then, which is also possible, but in theory, but then this formula would not work. All right, so how many of them are there here? It's 6. So the answer here would be 6 over 36, which is this. Well, so far the examples that we've discussed so far were all about two experiments combined into one composite experiment. Of course, we can extend this approach to any number of experiments. Suppose the same a coin is tossed 5 times. Okay. So we have 5 experiments combined in one composite experiment, And the sample space on each partial experiment contains only 2 outcomes, heads and tails. And how many outcomes are there in this composite experiment? So it's 2 to the power 5, which is 32. Okay? Any questions here? All right. Well, by the way, returning to the question of electing president and treasurer and secretary in a club that includes 10 members, we can treat the same question as as a composite experiment in a way. So we refer again to the example where a club, 10 members, and because it's a club of lovers of probability, they elect their leaders at random, or it's random choice. And what's the probability that 3 particular members will fill the first 3 positions? President, treasurer, and secretary. We can reason this way. We can treat this experiment, composite experiment, as consisting of 3 successive experiments. So the first experiment is choosing randomly a guy who will be president, okay, for the post of president. And the probability that if this is done at random, the probability that Smith will take this post is 1/10. Okay? But then let's consider the next experiment. The next experiment is making a random choice for the position of treasurer from among the remaining members, considering that Smith is already assigned to be president. And the probability that, and what was the name of the second guy? It was Brown. And the probability that that Brown becomes treasurer, given that Smith is president, is 1/9. Okay? And the probability that Jones becomes secretary, given that Smith is president and Brown is treasurer, is 1/8. And multiplying all of these, we get the same answer. Okay? So it's a slightly different approach to the same question. Here we talk about a composite experiment, but are these 3 stages of this composite experiment independent of each other? Well, the answer clearly is no, because when we elect one person for the post of president, at the next stage we have only a choice from among 9 remaining people. Already for this reason, the 2 experiments are not independent. Okay? All right. All right. Okay. So our next big concern is binomial distribution, so-called binomial distribution, which appears very often in probabilistic models and problems. And it's important both historically and in practical terms too. Okay, suppose we have a biased coin. So we specifically say that it's biased, not fair. And the probability of heads, let's say that it's 0.6. And we toss this biased coin 5 times. And the question is this, what's the probability that on these 5 tosses the coin will turn up heads exactly twice? So probability of getting 2 heads on 5 tosses. Well, this is not a very simple question, but it's an important question again because this example gives rise to the important formula of binomial distribution. Okay. Now let's try to understand how this can occur. 2 heads. Well, this is a possible scenario. Heads, heads, tails, tails, tails. Okay. What's the probability of exactly this sequence occurring? Well, now we make use of the concept of composite experiment. This is a composite experiment consisting of 5 stages, 5 partial experiments, and what's more, we assume that they are independent. So we can multiply probabilities. As a result, this is what we get. The probability of getting heads here is 0.6, and again it's 0.6 on the next toss, and this, and this are all equal to 0.4. Well, it's important that you understand this. Do you have any questions? Do you understand how it works? First, we make use of this data. We are told that the probability of getting heads on one individual toss is 0.6. This is piece of information number 1. Next, we assume that the consecutive tosses are all independent. Okay, so we can assign this probability to heads on each toss, and then multiply probabilities. So this is what we get. And multiplying this together, the numerical answer is this. But this is obviously not the only possible way of getting 2 heads on 5 tosses. Another possible way probably is this. H, T, H, T, T. Okay, so heads may appear on the first toss and the third toss. Well, obviously it's a possibility. The question is, what's the probability of exactly this sequence? And it's going to be 0.6, but the next term will be 0.4, and the next will be 0.6, and again 0.4, and again 0.4. And multiplying together, we get the same numerical answer. Well, is it an accident that the 2 answers are the same? Well, if you look at these formulas, you will notice that we should expect that the answer be the same, because, all right, the arrangement of T's and H's in this sequence and in this sequence are not the same. But in each of these 2 sequences, H appears twice and T appears 3 times. And each time H appears, we write 0.6, and each time T appears, we write 0.4. So no wonder that we get the same numerical answer, okay, as the product of this. All right, and which leads us to understanding that we'll get the same numerical answer for each possible scenario where heads appears twice. The question remains, how many different sequences like this there are, okay? In how many ways can we write 2 H's and 3 T's? Well, actually we know enough to answer this question now. Let me note that a sequence like this is totally determined in a unique way if we choose positions for the two t's, if we say at which two of the 5 positions heads, I'm sorry, for two heads, so 2 h's and 3 t's. If we specify the two positions in which heads will appear, in this way we specify completely, in a unique way, this sequence. Okay, so we know that the remaining 3 positions must be occupied by t's. And actually today we already have discussed exactly this. The answer is the number of combinations of 5 elements taken 2 at a time. So the number of different sequences like this is 5 choose 2. Okay. And if you want to compute the probability, we multiply this by this number, which is the probability of which such sequence. And by the way, what is this number here? It's 5 factorial divided by 2 factorial by 3 factorial, and this is 120, 2 and 6, and the answer is 10. So this is the answer to the question. Again, the problem was we toss a biased coin with probability of getting heads on each toss equal to 0.6. Well, this kind of coin is tossed 5 times, and what's the probability of getting exactly 2 heads? And the answer that we obtained is 0.23. Okay. Well, that was just an example, but it's kind of model example. It leads us to the general formula of so-called binomial distribution. But before we write this formula, let's give a definition to the concept of Bernoulli trial. Well, consider this very simple elementary experiment. It's this. Well, the sample space here consists of two outcomes, and quite arbitrary. One of them is called success, and the other one is called failure. This is a tradition in probability theory. Okay. Well, you should not give any serious meaning to these words. It's just a way to distinguish between the two possibilities. All right, and the probability of success is denoted by little p, and the probability of failure is denoted by q, and because there are only two outcomes and the sum of the two probabilities must be 1, q is equal to 1 minus p. And that's it. This is the most elementary experiment that we can think of, actually. And it bears the name of this remarkable mathematician, one of the founding fathers of probability theory. All right, it seems very simple. It's not as simple when we consider a series of such experiments. Okay? So now let's consider a series of n Bernoulli trials. Okay? And let's ask this question. Well, how many successes can occur on n Bernoulli trials? On each of the trials, we can get success or failure. In theory, on n Bernoulli trials, we can get no successes at all, 0, 1, 3, up to n. Okay, this is the complete list of possibilities. And accordingly, Okay. Now generalizing on this example, this is what we write. It's n choose R, the number of combinations of n objects taken R at a time, multiplied by p minus p to the power R times 1. Well, let's write it this way: Q and minus R. And this is a very important formula. Now, R here is the number of successes, and N is the total number of experiments, trials. So R here can take on values from 0 to N, and this is the complete. All right, so any questions about this formula? It's one of the working formulas in probability theory. It appears very, very often in different questions. All right, let's give it a simple example. Well, suppose a certain traveling salesman goes from door to door trying to sell a certain make of a vacuum cleaner. He's selling vacuum cleaners. And so vacuum cleaner. And from his own experience, he is successful 20% of the time. 20% of the time. Okay. Suppose this in a certain neighborhood, this traveling salesman visits 15 homes. What's the probability that he will sell exactly 3 vacuum cleaners? So 15 visits, and what's the probability that this traveling salesman makes 3 sales on the 15 visits? Well, this is exactly the case where binomial distribution works. Of course, we assume that this probability point 2 works always, okay? And the result of his second visit or third visit doesn't depend on the previous visits. So we assume independence, and we assume this constant probability of success. All right, 15 visits in total. The question is about 3 successes, and the probability of success is raised to the 3rd power. And also don't forget that we need to multiply this by the probability of 12 failures. So if 3 of the 15 visits are successful, then 12 visits are unsuccessful. Okay, so we do this 0.8 to the power 12. Okay. Now let me ask you, what's your guess? What's this probability? By the way, look at this. This guy is successful 20% of the time, and he makes 15 visits. So the average number of successes on this number of visits would be 3. So we ask the question about exactly this average number. Does it mean that the probability of getting 3 successes on 15 visits is something close to 1, such as 0.9 or 0.99? Well, absolutely not. Okay, it's just an average number, and with this average number, it's quite possible that he gets no successes on 15 visits, or 7 successes, or even 10 successes. Everything's possible, and the probability of this is, using the calculator, is okay, 0.25. All right, another example. You all know what a multiple choice examination is, okay? Multiple choice. choice exam. Well, multiple choice examination. Let's say that there are 10 questions on the exam paper, and for each question 5 answers are suggested. 5 answers, of which only 1 is correct. Now, suppose a student, well, there are such students, unfortunately, who don't know anything at all. And this particular student doesn't know anything and answers the questions at random. So he answers by picking one of the 5 options at random. Well, suppose this, there is this academic requirement that, well, this exam is considered as passed if the student answers correctly more than 50% of the question. So pass is more than 50% of the questions. Now, what's the probability of getting a pass if you answer these questions at random? Probability of a pass. Okay. Now, let's try to understand how you can get a pass in this situation. Well, by definition, a pass is more than 50% correct questions. So if there are 10 questions in total, then you need to get at least 5 correct answers. I'm sorry, 6 or 7 or 8 or 9 or 10. These are the pass. All these mean pass. So it's probability of 6 plus probability of 7 plus probability of 8 plus probability of 9, probability of 10. And how do we compute each of these? What's the probability of getting 6 correct answers if you answer these questions at random? Well, it's 6, 10 choose 6 multiplied by and it's 4. Look at this structure. I want you to understand it. This is the number of ways we can select 6 questions out of a total of 10. This is the probability of answering successfully any given question if you select an answer option at random. And this is the probability that you guess wrong. So, and the next term would be 10 7.2 to the power 7, 0.8 to the power 3, and so on. Okay, and performing this computation, this is the answer that we get. It's this. Roughly 6 times out of 1,000 you can be successful if you use this strategy. I don't think it's a high probability, so there is some moral here. Cheating doesn't pay. Crime doesn't pay. Okay. All right. If you don't have any questions, let's move on. We need to pace up. We're kind of lagging behind our schedule. As I mentioned earlier, the time frame allowed to us for this course is really very, very well. It's inadequate. It's just not enough to cover even the main stuff. All right. The next important thing is so-called Poisson distribution. Again, let's start with an example. Poisson distribution. Example. Suppose we make a cake, and the cake is going to have this size, 10 inches by 10 inches by 10 inches, okay, which is rather a large cake. And this cake has raisins in it. Raisins. Do you know what raisins is? Raisins. And there are, we use 200 raisins. Well, and before putting this in the oven, we mix the components up very, very carefully. And these raisins get distributed in a certain random fashion over the entire volume of the cake. Okay? And then after we've made this cake, we cut out 1 cubic inch. 1 inch cubed. And the question is this: what's the probability that a certain given number of raisins, say 1 or 2, will be found in this cut-out inch, in this given volume? Well, what is the mathematical nature of this problem? Again, I want to emphasize that we mix up the contents very, very carefully, and there are no clumps. Do you understand this? It's possible that the raisins stick together and form these clumps. Now, no, we take care to prevent it, okay? All the raisins are quite separate and distributed randomly. Well, if this is the case, that each individual raisin has a certain probability of getting in this volume. And what's this probability? So for each value, for each raisin, the probability of getting in a given 1 inch cubed volume is 200 divided by 1000. So because there are 200 raisins and the volume is 1000 cubic inches, which is 0.2. So each particular raisin can get into this volume accidentally, okay, with this probability. Well, let's pay attention to this product. The number of raisins and which is oh, I'm sorry. It's nonsense. I'm sorry about this. For each raisin, the probability is 1 over 1000. Okay, exactly. So for each particular raisin. And because there are 200 raisins in total, n times p is 200 divided by, and this is 0.2. And we can interpret this number as the average or mean number of raisins that we expect to find in a 1 cubic inch, okay? In a volume of 1 cubic inch. And we can use the binomial distribution here, the binomial distribution that we just discussed. I'm not going to write the formula, but just refer you to the formula that we just discussed. All right, another example. I want to use this example to build some intuitive understanding in you, intuitive understanding of the formulas that we use. Okay, suppose there is some small town, and this small town has 2,000 residents. Okay, and there is only one dentist in this town. Let's say that each resident of this town visits the dentist once a year on the average. So one visit to the dentist per year on the average. Next, let's assume that the residents do not visit the dentist in groups. Actually, in real life, that would be quite possible, that family groups come to the dentist. Let's assume that it's not what happens, okay? Every resident visits the dentist for his or her own reasons at some random points in time. All right, and there are no fixed schedule, okay? Some people who really take care of their health visit the dentist, say, twice a year on certain dates. Well, let's assume that people in this town are not so conscientious, not so cultivated in terms of health, so they visit the dentist in a random way, on random dates. All right, the question now is this. What's the given these figures, what's the probability that on a certain given day, the number of visitors to the dentist will be 2 or 3 or any other number, or 0, for example? Well, let's say that suppose there are 365 days a year, no leap years, so-called leap years, and the dentist does not have any days off, doesn't take any days off. He works 7 days a week, and the whole number of days is 365. So what's the probability for any individual resident, the particular of visiting the dentist on a given day? So for any resident, it's 1/365, because the residents visit the dentist once a year, and there are 365 days. But the number of residents is 2,000. So n times p, which is the average number of visitors to the dentist per day, is 2,000 multiplied by this, and the numerical answer here is 5.48. So about 5.5 visitors per day can be expected. All right, I'd like you to notice a similarity between these two examples. In both cases, the binomial distribution is applicable, but the probability of success is very, very small. Here it's 1/365. In the cake example, it's 1 divided by 1,000. So on the one hand, the probability of success is very small, but the number of experiments performed is great. 200 residents in the first example, 2,000 residents here. So we have these opposing trends, a very small probability of success and a large number of trials. But the product, n times p, is neither very large nor very small. It's 0.2 here, and it's 5.48 here. It's not 100, 1,000, or some very small number. All right, let's try to derive the formula. So let's look at the binomial distribution with very small probability of success on an individual trial and large number of trials. The formula is this for R successes on n trials. It's okay, which let's write it this way. It's n times n minus 1, n minus r plus 1, r factorial, and then we multiply it by p to the power r, and 1 minus p to the power n minus r. All right. Now, you all did a 1-year course of calculus. not so very long ago. And because I believe in my students, I hope you remember what limit is, what this calculus operation means, taking something to the limit. We are going to take this expression to the limit as n approaches infinity and p approaches 0 in such a way that n times p remains constant and equal to a certain, well, this is the conventional, the accepted notation for this product, and it has the meaning of mean. All right. Well, we rewrite it this way. Substituting p equal to lambda over n, we can rewrite it this way: n times n minus 1, n minus r plus 1 over n factorial, lambda to the power r over r factorial, and here it's 1 minus lambda over n, n minus r. Okay? It's just some manipulation, some algebraic manipulation if I express p through lambda over n. And now in this formula, lambda is kept constant and r goes to positive infinity. Well, those of you who are interested in calculus may look it up in a calculus textbook and find that this is the limit of this expression is e to the power minus lambda, and the limit of this expression is just 1. So the limit to this is, okay, and this is the probability of our successes for the Poisson distribution with mean lambda. And we have just derived it. We are just as smart as Poisson, who was a very, very brilliant French mathematician. Thank you. See you next time.